functions that are bounded and defined on a closed interval are the functions that we have considered in the definition of the Riemann integral. However, in many practical applications, it might be good to have a version of the integral that works for more general functions. Such integrals can be defined using sophisticated tools. For instance, the famous Lebesgue integral works for a much larger class of functions than those that are bounded and defined on a closed interval. However, the Lebesgue integral is quite difficult to define and is technically a part of a graduate course. What we are going to do now is to take a much more restrictive approach and define integrals for certain functions that might be unbounded or defined on an unbounded interval. This definition is going to be just a slight tweak of the definition of the Riemann integral and is therefore much easier to handle. As an application, we will use these more general integral to devise a test of convergence of series called the integral test. So let's move on to the definition. Let f from open A close B to R be a function that is integrable on close CB for all C coming from the open interval AB. So you're given a function defined on a one-sided interval. A, the point A is not really there in the interval. However, when you take any point C in the open interval AB and restrict this function f to the closed interval CB, you end up with an integrable function. Okay? If limit C going to A, I should say C going to A plus, because technically I want C to come only from the closed interval AB. If limit C going to A plus integral C to B f exists or is infinite, then we define the limit as the improper integral A to B of f. Okay, let me just add a remark. If the limit is infinite, it could be plus or minus infinity. If the limit is infinite, then we say the integral A to B f diverges. Otherwise, if the limit is finite, we say integral A to B f converges. Okay, so note carefully, integral A to B f could not exist at all in the first place. Then if it exists, it could either converge or diverge. If it converges, then the value is going to be a finite real number. If it diverges, it's going to be either plus or minus infinity. Okay, so where does such integrals come up in practice? Well, the best way to see that is to actually see an example of such an integral. Example, let's consider the function f of x equal to x power minus 1 by 3. Okay, and we define this on the interval open 0 closed 1. Okay, note that this function is not even defined at 0. Now let's see whether we can compute the improper integral of this function x power minus 1 by 3. Well, let's integrate integral c to 1 f. Okay, which is just integral c to 1 x power minus 1 by 3 dx, and from elementary high school integration this is just 3 by 2 x power 3 by 2, and I have to substitute the limits, which is c and 1, which is just going to be 3 by 2 into 1 minus c power 2 by 3. Okay. Now as c approaches 0 plus, clearly the above limit is 3 by 2. Above limit is 3 by 2. Okay. Therefore integral a to b f converges. So the improper integral of x power minus 1 by 3 on the interval 0, 1 exists, and in fact this integral converges, and the value of the integral is going to be 3 by 2. Now let's see an example where the improper integral diverges. For this, take g of x equal to 1 by x, again for defined on open 0 closed 1. Just judging from the graph, you would think that this integral, improper integral, does not exist. But let's check that rigorously. Again, we have to compute integral c to 1 by x. Again, from elementary calculus that you have learnt in school, this is just log 1 minus log c. Okay, and which is just minus log c, because log 1 is 0. Now as c approaches 0, this minus log c sort of diverges to plus infinity. Okay, so in other words, integral 0 to 1 by x is plus infinity. Okay, now if you have been following what I am saying carefully, the following question would have arisen to you. Suppose I start with a function f from ab to r, and let me write it as closed so that there is no confusion. It's closed ab to r, which is integrable. Suppose I take such a function, then there is absolutely nothing stopping me from considering limit c going to a plus integral c to b f. Okay, think about why integral c to b f is also defined. It's rather easy why it is also defined. So let's look at limit c going to a plus integral c to b f. What is its value? What is its value? Okay, so to understand this, I'm going to give you an exercise. Suppose f from ab to r is bounded and limit c going to a plus integral c to b f exists. Note, implicitly when I write limit c going to a plus integral c to b f exists, I am assuming that integral c to b f exists. In other words, for all points c in open interval ab, I am assuming that the function f, when restricted to closed interval cb, is integrable. Not only is it integral, I am assuming that the limit exists. Then integral a to b f also exists. Okay, now that I think about it, I don't need to put this extreme restriction, and I can just assume integral c to b f exists for all c in ab. That's enough. So if you have a closed interval ab and a bounded function f on that closed interval ab, and suppose you have that for all points c in between a and b, integral c to b f exists, then integral a to b f also exists. So in short, what this is saying is, the improper integral, you need to tackle the special case of improper integral only under the condition that the function f is not actually bounded on the interval ab. So to clarify that, let me also remark the value of this integral, value of integral a to b f, does not depend on does not depend on f of a. You can set f of a to whatever you want, the value of this integral will continue to be unchanged. Okay, so please solve this exercise. It is important and let you understand why exactly we are defining improper integrals the way we are. Okay, now there is no difficulty in generalizing this notion of improper integral to intervals of this form, f from ab to r, that need not be bounded. It's exactly analogous, that need not be bounded. You can define for, just like the left hand point not being there in the definition of f and the function being unbounded, you can consider f from closed a open b to r in the exact same way. One other case remains, that is functions that are defined on infinite intervals. Definition. Let f from a infinity to r be a function such that f from ac to r, or rather I will not use this notation, f restricted to ac is integrable for all c greater than a. Okay, so what I'm doing is I'm considering a function that is defined on a one-sided infinite interval such that whenever you take a finite quantity c and restrict the function to the closed interval ac, the function f is integrable. Then if limit c going to infinity, you should guess where this is going, integral a to c f exists. Okay, by exists I could mean it could be finite or infinite. The limit either converges to a finite quantity or it goes to plus or minus infinity. If this happens, then the improper integral of f on closed a open infinity, and again this is denoted by a infinity of f, is defined to be integral a to infinity of f is equal to limit c going to a plus integral a to c f. Okay, now let's see an example. There's nothing really great about this definition, but let's see. Consider the function g of x to be equal to cos x. Consider the function g of x equal to cos x, and we are going to define this on close 0 open infinity to r. This is a bounded function, remember that. Okay, of course integral 0 to c cos x is nothing but sine c minus sine 0, which is sine c. Okay, so the function cos x is integrable for any closed interval of the form 0 comma c. That's straightforward and obvious. But limit c going to infinity of sine c obviously does not exist. Okay, therefore the improper integral integral 0 to infinity cos x does not exist. Okay, so we cannot assign a sensible meaning to integral 0 to infinity cos x. Again, this is expected sort of from the graph. If you think about the graph of cos x, it will be clear to you that one cannot actually expect this function to be integrable in any sense. Let's see another example. Consider f of x equal to x power minus 2 for x greater than or equal to 1. Okay. Now let's try to compute integral 1 to infinity of this function f. Okay. Now let's take integral 1 to c x power minus 2. And again from basic calculus, this is just minus 1 by x, and the limits are 1 and c, which is just 1 minus 1 by c. Okay. Now as c approaches infinity, this above quantity converges to 1, which means integral 1 to infinity x power minus 2 exists and equals 1. Okay. So the best way to make sense of these improper integrals is to actually draw the graphs of the various functions that we have considered and to see which type of functions seem to have improper integrals and which type of functions don't seem to have improper integrals. In the next module, we will apply this basic theory to prove a nice test for convergence called the integral test. This is a course on real analysis, and you have just watched the module on improper integrals.